Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
So here's the outline of my presentation. I will first give you an introduction to the main idea behind the complexity notion that I developed within my PhD, basically, in 2001. And later on, it turned out that it's very related to integrated information as proposed by Giulio Tononi. And so I will report on more recent work on the relation between complexity based on information geometry and integrated information. After that, I will give you an overview of morphological computation measures that we developed in order to argue that the higher the morphological computation is, the lower the integrated information will be, which for me generates some problems here. So one way out could be learning. So I will motivate this, why learning is important, and then outline ideas on how we can actually get integrated information back into the theory. So let's start with the notion of complexity. That's the famous quote. The whole is more than the sum of its parts. That's the idea of complexity. And to be more precise, complex systems are systems where the collective behavior of their parts entails emergence of properties that can hardly, if at all, be inferred from properties of the parts. So I'm going to show you a pseudo-theoretical approach to this phrase here. So you see all kinds of mathematical symbols here, but it's more about the geometric concept, to highlight the geometric concept in order to formalize this idea of complexity. So let's say we have a set of systems denoted by calligraphic S, and we want to measure their complexity. So first of all, we assume that we have a map denoted by D, which basically takes the system and decomposes it into its parts. So D stands for the decomposition. Then, based on that on the set of parts, you can try to compose these parts again to regain the original system. Of course, in this composition of decomposition and composition, you will lose some information. But if you do this, if you decompose and then compose back, you will generate a set in the original set of systems, which basically stands for those systems that are not more than the sum of their parts. So these are the non-complex systems. Given a system, you can now quantify complexity as the distance from being non-complex. So it's the distance from that set that I denote here by calligraphic N. So, and we want to interpret this as a projection. So it's S is projected to P of S, and P of S is in this set of non-complex systems. And the distance from the set N is here on the right-hand side, is the infimum over all distances between S and S prime, where S prime is taken from calligraphic N. And this equation here, this equality, is basically a consistency equality between the projection that we want to consider and the divergence, the distance measure D. So we cannot take any distance measure here. So it has to be compatible, so to say, with the projection. So that's the whole idea of how to quantify complexity as the deviation from the set of non-complex systems. That's the general measure of complexity. As I said, this is not at all specific. It's also not theoretical or mathematical. So you have to specify all these geometric concepts. And information geometry provides an excellent theory for actually formalizing this whole idea. And let's jump directly to the information geometry of Markov chains. Markov chains are conditional distributions. Let's say you have a set of n elements. I'm sorry, n stands for the time here. So you have a set, the state space, the elements of the state space is denoted by x. And the index stands for the time. So that's the state of the system at time 1, and that's the state of the system at time n. So you can unfold this. You can get the joint distribution of this trajectory, the distribution of this trajectory by taking first the initial distribution, P of x1, and then multiplying with the conditional distribution. So that's the conditional distribution, which is referred to as Markov kernel in mathematics or stochastic matrix. So you can unfold the joint, the whole distribution in time, and you get this joint distribution generated by the Markov kernel. And let's have a second generator of a distribution by a generator in terms of Q. And this way you get two joint distributions. You can now take the Kullback-Leibler divergence of Pn and Qn and divide by n. This can be written as the Kullback-Leibler divergence between the initial distributions plus this sequence here. And for n to infinity, if you assume ergodicity here, this will converge to this notion of Kullback-Leibler divergence for the stochastic matrices. So, in short, that's the distance measure that we want to use for the Markov kernels. So, in the space of all Markov kernels, and P denotes the stationary distribution of this stochastic matrix here. So here I have a plot. So this is not the space of Markov kernels, but the space of probability distributions. As you know, this is a simplex. So these would be the Dirac measures. The corners here would be the Dirac measures. And now you have actually a concrete set of non-complex systems. So you can actually write down the formula for that. And you can compute the complexity of a P simply by taking the minimal distance from that set, P hat. So that's the whole idea. So what should be the non-complex systems in the context of Markov kernels? So let's have a graphical representation of them. So the general Markov kernel is given. We now restrict attention to two elements, x and y, to make it simple. And x and y makes the transition to the next, within one time step, to x prime and y prime. And all transition probabilities from xy to x prime, y prime can be represented graphically in terms of the theory of graphical models theory in this way. So you have directed edges, and one undirected edge in the output. So what would be the non-complex system? The non-complex system will be a system where the parts evolve or generate their own state independent of the other elements. So for example, x in generating x prime does not look at y, and y in generating y prime does not look at x. So that would be the system that is not more than the sum of its parts. So you can see it here. So that's the overall transition from xy to x prime y prime. and it can be written as a product of these individual transitions, which means that the whole is nothing but the sum of its parts, where the sum is represented here in terms of multiplication. But if you rewrite it actually as an exponential family, you see the sum in the exponent here. So this is really the set of non-complex systems in the sense that these are the transition probabilities determined completely by the individual transition probabilities. And now you can define the complexity. So I denote the set of all Markov kernels of this structure by split kernels. So that's the set of split kernels. And then you can define the complexity of a transition matrix simply as the minimal distance from the set of all split kernels while using the Kullback-Leibler divergence that I have presented. So that was my general ansatz in 2001. And the nice thing about it is that you can explicitly compute it. You get as a complexity measure the sum of marginal conditional entropies minus the global conditional entropy. So it has very much the structure of multi-information that you might know. So this is a nice entropic representation of the complexity. And another nice feature is that if the transition from t to t plus 1 is compatible with a network structure, like in a neural network or so, in being more precise, if the transition from x to x prime has this structure, where you have an underlying network, the parents of I is denoted here by this symbol. They provide information to xi. So if you put in this structure into the equation, the above equation, then you end up with the sum of all these conditional mutual information. So basically what it says is each node looks at its own state xi while generating xi prime. It has the following information. It has information from its parents and it has information from its own current state. And that quantifies the information that is actually coming from outside. So that's the local extrinsic information entering the system. I refer to it as information flow. So basically the complexity is then nothing but the sum of local information flows. That was also a nice feature because I was at that time, and still I am very interested in information on the so-called Infomax principle for learning. Okay. It turns out that this is related to the general idea of integrated information proposed by Giulio Tononi as a measure of consciousness. And as you all know, there's a lot of work in that direction. A more recent work is actually trying to set up postulates or axioms for a phi measure that should be satisfied by any phi measure. Phi is the general term for integrated information without specifying it here. So if we are looking for a measure of integrated information, it should be, and it quantifies somehow the total information integration in the system, then it shouldn't be exceed the total information flow in time. So this capital N is not the time, so that's the global state of the system. So we have, for example, capital N neurons at time t, and we have capital N neurons at time t plus 1. And that's the mutual information in time. The integrated information shouldn't exceed that number. That has been postulated in this work by Oitsumi, Tsuchiya, and Amari. And now you can test my original complexity measure, whether this is satisfied or not. And it turns out it's not satisfied. So my complexity measure, which has this entropic representation, is upper bounded by the mutual information plus the multi-information in the output. So the correlation in the output that might actually come from extrinsic influences is incorporated into my complexity measure, which is not surprising, but it does not correspond to the general idea of integrated information. So the integrated information idea should only, integrated information should somehow capture the intrinsic information integration. So one direct way to actually overcome this problem is, if you want to have as an upper bound the mutual information, you can simply subtract from the complexity this multi-information, and some people call this synergistic information. So let's take the complexity minus the multi-information. That's a straightforward way to deal with this problem, but it doesn't lead very far, because the measure that you then get can be negative. So that's the problem. But the information integration should be positive. So Amari came up with a new way to actually deal with this problem and still have this mutual information as an upper bound. So let's consider again the set of general Markov kernels. And he said, just taking this arrow and this arrow for the split kernels is not enough. So in my previous notion of a split kernel, I had only these two, but I did not have this edge here. So he said, in order to cancel out the stochastic dependence in the output, you should include an edge here, an undirected edge, and it's incorporated here by this term. When you then measure the distance from such a model, graphical model, this will be smaller, and this will actually, by definition, be upper bounded by the mutual information. So now we can do the same complexity idea. So you have a modified complexity. You take the minimal distance of a stochastic matrix from the set of split kernels of second kind, so of this kind here. And it turns out, by definition, it's smaller than my original complexity measure, because the model here, the set of split kernels, is greater. So the distance will be smaller. And it's upper bounded by the mutual information here. So it's really a nice idea. And it turns out that it is more difficult to evaluate. There is no direct entropic representation, but you can actually deal with it by using the so-called iterative scaling algorithm. So here's a plot that we did in a joint work with Max Campbell. So you have 4 graphs here. The first one is the mutual information, which should be this upper bound. The second one, the green one, is my original complexity measure. The third one is the one proposed by Amari with this undirected edge in the output. And this one is this synergistic information, where you just subtract from the complexity the multi-information. So which I already said it can be negative. So you clearly see this behavior. So so that's a nice relationship here. But you see also that our measure, my original measure, is in this example below, is smaller than the mutual information. But what Amari was referring to is this phenomenon here, that my measure, number 2, can actually exceed the mutual information. So it can actually assign more complexity, more integrated information that is than the mutual information in time, the full mutual information in time. And you see how nicely this measure number 3 stays below the mutual information. So that's really nice. But there's a problem with it. So, this problem is actually led to this refinement of this work by Oitsumi, Tsuchiya, and Amari. They said the reason why for taking this kind of model is to have some complexity interpretation of it. So Giulio Tononi also in his works always refers to complex, causality, to the causal aspects of information integration. So information integration is, the very nature of information integration is causal. So therefore, we should somehow interpret the edges that we removed here as causal edges. And we would like to have the absence of these edges to be reflected by condition independent statements. So given that we don't want this arrow here, we would like to have that x prime is independent of y given x. So that would be this, this property. And the absence of this arrow should correspond to y prime is independent of x given y. The problem is that in this graphical model, that doesn't hold. So simply because, so let's test this arrow here. X prime, you can reach from y to x prime, you can go from y to x prime without the necessity of going through x. You can simply go this way, okay? This is why this condition is not satisfied. Therefore, in their work, they said, okay, but that's the most important condition. So let's have these conditions, which somehow capture the causality. We want, with this property, to remove all these arrows that define the integrated information. And this is how they define their split model. So with this property here. Now we can ask the question, if they want to capture causal aspects within the theory of Peirce's theory of causal networks, there's always a correspondence between conditional independent statements and a graphic and a graph, directed acyclic graph or chain graph. So there is always an interplay between conditional independent statements and the graphical representation of these condition independent statements. Now you can ask the question, what is the graphical representation of these condition independent statements? It turns out, and that's the main point here, that there is no graphical representation. So you can set up these condition independent statements, but they don't really reflect the causal structure in the sense of Peirce. So therefore, we propose a different approach. We, together with Carlotta Langer, we developed the following notion of a split model. Originally, Amari introduced this undirected edge here in order to cope with external influences. So if there are external influences which generate stochastic dependence here, we don't want to actually count them. And because that was exactly the problem with my measure. So we incorporated here, we added an external influence explicitly. And then we marginalized out this external influence. So if you look at this graph here, you see that for this graphical representation, these condition independent statements are satisfied. So if you marginalize out, you end up with something that is called a chain mixed graph. So instead of having the undirected edge here, you have a bidirectional edge, which has a very specific semantics. But in particular, it satisfies this kind of graphical model, satisfies this conditional independent statement. So instead of just writing down these conditional independent statements, we explicitly define a new split model in this way, and a corresponding integrated information measure. it turns out that this split model is the largest model that is contained, that satisfies these conditions and contains my original model that does not have this undirected edge. So it's an extension. The set of split kernels is extended, in the original sense, is extended in a way that keeps these condition independent statements. And that allows us actually to have, again, an interplay between condition independent statements and graphical structure. And so we did actually the calculations, the plots, so on these measures, so you can compare. So the blue one is the new measure, and the red one is the measure proposed by Oizumi et al. So ours is larger because it's a sub-model of their model, which is representable in terms of a graph. And again, you see the mutual information, that's the black line here, stays above all of them. The red one is the one that Amari proposed with his undirected edge, not bidirectional edge, but an undirected edge in the output. So we have a set of measures here. So my hope is with these slides to somehow convince you that information geometry can actually help in developing interesting measures of information integration. But so let's critically discuss this this notion of information integration. So several years ago, Giulio Tononi visited us in Leipzig, and I actually asked him explicitly. I said, look, I'm working on embodied systems. You always look at these isolated systems and compute the integrated information. That's nice. And you specify the network structure with high integrated information. Did you ever think about systems actually interacting with the world? So how would integrated information behave there? For instance, within the field of embodied intelligence, people actually try to outsource computation, referred to as morphological computation, so they wouldn't like to integrate their information internally. So what do you think? Do you think that embodied systems that interact and outsource computation would still have high integrated information? And his immediate, let's say after 2 or 3 seconds reaction was, no, that should go down. So the integrated information should go down if systems are outsourcing morphological computation. And since then, we actually developed the theory further, and I'm going to show you some aspects of our analysis here. So I will first try to give you an overview of our approach to morphological computation, and then maybe relate the two to each other. So systems, as I said, interact with the world. They are not isolated. So you all know these examples. So that's a system with high computation, a lot of computation that is required for generating some behavior, that some naturally looking behavior. And you have these systems that have no computation at all, which generate similar behavior. In particular, such a system with no brain will not have any integrated information. So there is another set of experiments that we did in connection with grasping. Grasping can be actually quite difficult in robotics. There are, within soft robotics, the field of soft robotics, people are actually developing methods to reduce the control. So this control is here. That's, by the way, a hand developed by Oliver Brock. And it works simply by air pressure. So when you set air pressure on, you have this grasping behavior. And due to the compliance of the fingers, it's able to grasp different objects. So again, very low control. So I want to show you another example that we did many years ago. which I find fascinating. So it's a toy example. So you have these little robots here, 7 of them, and each of these robots has 2 wheels, and the wheels are controlled, let's say, by some brain, by tiny brain, and so you don't see the brain here. It's a neural network. I think it's consisting of 2 neurons, and they control such a segment, such a small robot. And with this control, you can look at the, observe these robots, what they do. And so again, I didn't show you the brains. I just show you the behavior in physical space, and you don't see any coordinated behavior. It looks like Brownian motion, but believe me, there is a brain controlling this Brownian motion. And now we do the following: we couple these segments. The brains remain the same. So every segment has its own brain. So we have 7 split brains here. And by this physical coupling, the system starts to coordinate and to show this coordinated behavior. If you look at it and you intend to control this whole thing in terms of one brain, you might think that high integrate information might be required because it's complex behavior. But remember, we did not couple the brains of these agents. They are split, so no information exchange at all. Everything is emergent through this physical coupling. So if you call this kind of behavior intelligent, then it would not involve any integration of information within the brain. So that's the kind of phenomenon I'm referring to. So let's try to quantify this phenomenon. So we refer to it as morphological computation. Don't kill me for these terms. There are many debates about it. I have no better name. So what is computation? Does physics compute? It's a whole other debate. I'm using this term being aware of this critical meaning of the term computation. And also, it does not just refer to the morphology. It has been called morphology. Some people now call it physical computation. So it's a general term for the phenomenon I'm just describing here. So let's look at this piece of sensorimotor loop. So you have the transition of the world state from W to W prime and the action A. And the transition takes place, so there is a transition map, a stochastic map, or Markov kernel from WA to W prime. And now you can decompose this Markov kernels into pieces. You can first remove. So first of all, you can represent it this way. So it's a conditional distribution of W prime given W and A. It can be represented this way. And this, in this exponent here, the terms in the exponent are sometimes referred to as interaction in physics. That the term comes from physics. So that's the interaction potential here. And we have unique terms. So W prime only takes information from W. W prime, that's the interaction with A, that's the interaction with W, and that's the synergistic interaction with W and A. And this is what in neural networks theory you refer to as the bias. In physics, you refer to as the magnetization. So that's the tendency of the output without having any knowledge about the input. So now you can, according to this, you can decompose the whole transition and first remove the synergistic part. So that would be the graphical model. And with this, actually, you associate the whole exponential family in information geometry. So in order to quantify, for example, the synergistic contribution, you would measure the distance from this to this. So what is the effect in behavior space, if you wish, of this higher order term. So you can measure this, and that's we refer to this as synergistic information. You can further decompose by removing this arrow here or this arrow. And then the final decomposition is by removing all arrows. So now the Kullback-Leibler divergence from the left, this graph to this one is exactly equal to the mutual information between WA and W prime. The Kullback-Leibler divergence from this one to this one here is the conditional mutual information of W prime given A, and from here to here, it's the conditional mutual information between W prime and A given W. And from here to here, I already told you, we call it synergistic information, but that cannot be explicitly computed. You need this iterative scaling method for that. So here's the Kullback-Leibler divergence. And now you can actually use this in order to define all kinds of morphological computation measures. For instance, you can say the extent to which the action is synergistically operating on W in order to create W prime. That's the morphological computation. You can also say it's basically the strength of this arrow, which is quantified by this. So it's from 1 to 3, the distance from 1 to 3, it's the strength of this arrow, but that's control. And you want to have the opposite of control. So you write it down as some upper bound minus something that I call morphological computation here. So that's the second way to quantify morphological computation. You can actually directly measure the effect from W of W on W prime given A, which is the distance from 1 to 4. That's also morphological computation. It's denoted by MCW. And then there's a last one. So you see there's a whole spectrum of possibilities here. We tested them in an experimental setup and realized that until now, the one that is the easiest one, the conditional mutual information, where you simply quantify the strength of this arrow here, it's the distance from here to here, turns out to be the most useful one. Here's an experiment just to show you. So we have a muscle model behind this. I will show you the muscle model. And the muscle is forced to actually generate some hopping behavior. So the hopping behavior is prescribed. And then we measure the morphological computation in time. So it's plotted here. So the hopping behavior, this movement has two phases. One is the flight phase. In the flight phase, only the physics works. So the morphological computation is high in the flight phase, here in the blue phase. The stance phase is actually initiated always by low morphological computation. That's the region where you actually need control. You need explicit control in order to keep generating this movement. So the control is really taking place at in the beginning, at the end of the stance phase. And this is quite nice. And we compared this, so that's the model, by the way. It's a well-known model. So you basically consider forces, the forces at the muscle, and that's the force. It has two components. It's the component depending on the position and the component dependent on the velocity. And then you have the control signal here. And now you can choose f of y and f of y dot according to different models of various complexities. So you can choose them simply constant. So I think that's the first term, that's this one here. We have three choices here. And for the second one, we have also three choices. So we have nonlinear, nonlinear, linear, linear, constant, constant, and we can have all kinds of combinations. The one that I have shown to you in the previous slide is nonlinear versus nonlinear. So it's the most flexible muscle that you can have. And we compared this with the following. Here we had this nonlinear muscle, which I have shown to you. Here we had constant versus linear. So this has restricted flexibility, but it's still the same model. And then we took a DC motor, so not a muscle anymore, and we computed for all of them the morphological computation. And intuitively, we were actually happy to see that the one that is most realistic, this one has the highest morphological computation. So it's 7.2, and this is these are lower values here. Remember, all of them were forced to do this hopping behavior. Okay, let's come back. So that's so far about the morphological computation measures. So we took now these morphological computation measures and tried to relate them to integrated information. And we did this until now. This is ongoing work primarily with Carlotta Lange, who is working within the DFG priority program, the active self. And we have this experimental setup here, where we test integrated information and morphological computation. So the experiment is the following: you have walls here, obstacles, and these creatures are forced to go through these around these walls without hitting them. When they hit them, they die. So you see, then they are highlighted in red. In order to navigate, they have two sensors. These are the sensors. And we considered several lengths of the sensors. So the sensors go from 0.5 to 2. So this is the length. So if they are, for example, 1 meter, let's say this is in meter, 1 meter away from one of the walls here, they will not be able to sense the wall. With these sensors, they will be able to sense it and then feed back to their motor commands. To their control. So let's see. So this is how they move. So you see the red one when they highlighted in red when they die, and when they detect a wall, you see it in green. So that's the whole setup. The control architecture is the following. So we consider the sensorimotor loop here. Here's the world. And then they are equipped with sensors, with actuators, and with an internal state, the brain, basically. And in order to be able to actually measure integrated information, we need a compositional structure. So the sensors are actually subdivided into two binary sensors, which at each time step. So we have two binary sensors at time t, the same two binary sensors at time t plus 1, the same with the actuators and with the controllers, controller neurons. So now we did the following using methods from information geometry, more specifically the EM algorithm. We could actually compute the optimal policy to survive. So the optimal policy is obtained not in terms of learning or evolution, it's obtained in terms of this EM algorithm. So we have ways to actually get the optimal policy. Having the optimal policy, you can then plot the integrated information for the optimal policy, and you can also plot the morphological computation. And this is what we get. So I forgot to say that we do the plot in dependence of the length of the sensors. So we increase the length of the sensors and give them more possibility to observe their environment. So if you increase the sensors, the morphological computations then increases, so they can exploit more in order to navigate, because they are equipped with more sensors, with more powerful sensors. But at the same time, there is no necessity anymore to integrate information within the brain. So the integrated information goes down. So this exactly confirms Giulio's original immediate idea that actually outsourcing computation will reduce integrated information. So on one hand, it's nice. So we confirmed, and as I said, this is an ongoing work. But on the other hand, what does it mean? And that refers to the zombie in my title. So does it mean if we are intelligent in the sense of embodied intelligence, we are not conscious anymore? So we are zombies. So that I don't like that idea, even though it's hard for me to find any arguments against it. So that's my current struggle. So I'm trying to find arguments against this picture here. And so here are ways out maybe of this dilemma. First of all, let me highlight the importance of learning. So as I said, we obtained the optimal policy in terms of an EM algorithm, from information geometry. There was no evolution, no learning, nothing. But is that realistic? Clearly, we need more. And here's my take on why we need actually learning. The system is interacting with the world through sensing and acting, through its sensors and actuators, and generating this way behavior, okay? So the mechanisms in the sensorimotor loop can be, there are two kinds of mechanisms. There are intrinsic mechanisms like phi and pi. So this somehow controls the internal dynamics of the brain state, and the pi controls the interaction with the it's the policy controlling the effect on the world. So this is the policy and this is the internal dynamics. So these are intrinsic mechanisms that can be modified by the system. But then there are extrinsic mechanisms, alpha and beta. Beta are the sensors. So you are equipped with the sensors, but you are also equipped with the alpha, which incorporates somehow all the properties of the body and how your body interacts with the world. So that's the physics. So generally, or originally, I was thinking that's fixed. So the embodiment constraints sigma, which consists of the pair alpha and beta, are fixed. And within these constraints with your body, you have to find the best control mechanism. But actually, that's not the whole story. The embodiment constraints are not fixed at all. So we have growth, we have development, and we have aging. So our body is changing all the time. So that means that our embodiment constraints change all the time. Also, the environment changes. And there could also be more drastic changes of our body, like limb loss. And our brain has to cope with that to some extent. So adaptability to these external perturbations should be implemented in the brain in order to cope with these situations, to recover the original function. But there is not only external perturbation of the body and the environment, there is also internal perturbation. And that refers to a theory of robustness that I developed with David Krakauer and originally, and further developed with Jessica Fleck from the Santa Fe Institute, and Johannes Rau, and further students of mine. So the idea is the following. In addition to having external perturbations, changes of your body, you can also have internal structural perturbations. So the system then, if it's able to generate some behavior, it might not be able to generate that behavior anymore. So the system should be equipped with adaptation mechanisms to regain the original function as consequence or in response to internal structural perturbations. And for that, we developed the theory of robustness. We call it network robustness. So you basically remove components and you insist on still having the ability to recover the original function. And it was quite surprising to actually rediscover the TSE complexity in this context. So that's an old work from 2007, together with Jessica Fleck and David Krakauer, where we could prove that the robustness measure that we have for being able to cope with structural perturbations is actually upper bounded by the classical spatial TSE complexity, which was something like the sum of, you subdivide the system into two parts, and take the mutual information, and then you take the appropriate averaging over all possible bipartitions. That was quite surprising. So it basically says, if you want to have robustness, temporal robustness in time, so that's a functional network actually, it's acting in time, and if you wanted to to keep its function after removal of components, then you have to generate some redundancy in space. That's an important point. It's not in time, it's in space. So that's the corresponding image here. So this is the whole system at t, and this is the whole system at t+1. In order to keep, and you want it to be robust against knockouts of these edges, let's say, then you have to create here redundancy, spatial redundancy. And that redundancy should have this structure. That means if system evolved in a way that they can cope with intrinsic perturbations that are robust in this sense, then they have to display this property of high TSE complexity in their patterns that they generate. That's nice, but it's not the kind of integrated information that I was talking about until now. In the original paper where TSE complexity was introduced, they did not distinguish, they had implicit in mind that there is time, okay? You take this bipartition and one component corresponds to time t and the other component corresponds to t+1. You inject noise in one component, and after one time step, you observe the complement. There was implicit in time, but the whole derivation was made completely in a completely spatial way. So it was a measure defined for space, spatial correlations. And that's what we get here. It's not the temporal domain of integrated information. So, and this brings me to the last notion, maybe an alternative way to get time into the whole discussion back. We should extend the network. So until now, I talked about this policy pi here. The policy pi can be very cheap with low integrated information. But it seems there's indication or strong evidence that whenever you have to have learning mechanisms involved, you need to be able to predict the next sensor input. So you basically perform an action and predict the next sensor input, and you want to compare the two and have the small distance between the two. So in other words, you have to build up a so-called world model. So it could be that pi itself, which generates the behavior, as you can see, the world model itself does not have any influence on the behavioral patterns that you have in the world. It could be that while morphological computation reduces the integrated information for pi, it might at the same time actually require high integrated information for the prediction processes. So that is referred to as forward model in robotics, for example. And then there is also an inverse model for deliberative action. So if you want to achieve as the next sensory state, you act in a particular way to increase the probability of observing S. So these inverse models, so you have a forward and an inverse model, they both might actually contribute to integrated information. But to conclude, integrated information always refers to a compositional structure. We don't have a compositional structure here. Therefore, currently, we are actually fleshing out this structure, this forward model and inverse model in terms of a neural network, and trying to identify the integrated information there. So even in the setting that we considered, where we computed or derived the optimal policy pi for optimal navigation, if you insist on having also the possibility to predict the next sensor input, that might again reintroduce high integrated information. That's an open problem at the moment. So with that, I would like to conclude. One final remark. So as already pointed out, I'm going to start a new institute at the Hamburg Innovation Port. That's the vision of the innovation port. It's not built yet. There's only HIP1 built. It's this building here, and my institute will be located there. And I'm currently looking for people for that institute, and specifically for a postdoctoral researcher with mathematical background who can take responsibility for building up a robotics lab. So I want to actually extend the research that I have presented today to real robots that interact with the real world. And that would be one aspect of the mission of the institute. So if you have questions on that, please write me email to me. Thank you very much.